Morning, everybody. Glad to see you out there. Hope everything's going well. I have been having some stream problems, so hopefully this one's gonna run good, run well, or better than my last one. So let me know. I have you on a little bit of a delay, so that might be so if you ask a question in the chat, then I will try to respond as quick as I can, but you might find there's a little bit of delay between when you ask the question and when you see the answer coming up. Let me know if you're having any trouble or if the stream gets too jittery on you, and I'll see if there's anything I can do on my side. All right, so a couple things have happened. I have posted a final assessment for kinetics. That assessment is up on your Google Classroom. Still having some video. Go to advance. I'm gonna check some things here. OBS preferences. Advanced. Okay. Still having some health problems with my stream here. I'm just gonna go dark for 1 second and see if I can see what's going on here. Nothing is obvious here. Almost feel like I have to just restart my computer here. OBS streaming. Okay, well, we're just gonna hope that it's good enough. Okay, so for the test, we're going to I need it back by April 6th, so that I can include that final assessment into your midterm mark for for your report card. Apparently, we're still going through with midterm report card grades, so we're gonna go with that, and that's what we're gonna have to go with. So it'll be based on those first 2 units. Anything you want to do, any assignments that I've posted, please complete those by April 6th. So that's complete any assignments that are posted that you want to complete by the 6th. So I know that we're getting into spring break here, but if you can find some time to get in there and check and do that, that would be. Maybe I was trying to stream it too high a value there. Okay. All right, so let's get into this. We are into equilibrium law calculations. This is the majority of the, are you doing live stream? Yes, we're gonna start the live stream right now. So yeah, we are starting now. I had some bad connections. Oh, yeah, so that's an interesting question about live streams during spring break. but classes are technically over during spring break, so we don't have any requirement to hold class. What are people's thoughts? Do you want more class time in spring break? Do you want live streams? I am also trapped at home, so it does seem like it's possible, particularly for this class. I wouldn't be against doing some streams to catch up a little bit. But that's sort of on you guys if you want to be coming back to class, if you want to have these live streams during the week. Yeah, let's get here's some thoughts. Any thoughts on having classes through the spring break? We are technically not required to hold class, but we could use the time to catch up. Does anybody want a break? It's completely within your right to want a break. There's enough things going on in the world that having extra class time is not necessarily high on the priority list. Okay, I have no idea why. Any thoughts? No thoughts. Okay. Well, let's get into this then. If you want to drop a message in the notes, then I will appreciate it. Let's see how it goes. So we're going to now calculate some equilibrium constants. So there are a couple of different variations of these questions that we're going to use. I posted the answers for the previous class in the previous lesson. I'm just going to check one last thing here. Let's see. Still doesn't look great. I don't know, something is using up bandwidth in my house, and I'm gonna just turn off my phone. Okay. All right. So this the first type of question. Sorry for all this these technical glitches here. All right. So the first type of question is going to be this type where you are given the equilibrium concentrations, and you're asked to calculate the value for K. So you can calculate the value for KQ if you're given the concentrations of the reactants and the products at equilibrium. So we were talking about at equilibrium. These values are then substituted into your equilibrium law. So we have to write out our equilibrium law first. So EQ law. So in this example, we're going to put our products over our reactants raised to the power of their coefficients. and that is equal to KEQ if you're talking about equilibrium concentrations. So a container, a 2-liter container, holds 0.00040, 0.15, and 0.50 moles of these chemicals. So we need to find those equilibrium concentrations then. So NH3, we're looking for equilibrium concentration. NH3, N2, and H2. If it's been a while since you talked about concentration, remember that concentration is the number of moles divided by the volume. Number of moles divided by volume, number of moles divided by volume. So if they are telling you that there is, for NH3, there's 0.5 moles divided by the 2.0 liters, then they are telling you that there is a concentration of 0.25 molarity at equilibrium. Same idea, we can take our N2. N2 is 0.040 moles divided by 2.0 liters, and that equals 0.020 molarity. Just stop me in the comments there. If I've got the comments open, so if you have any questions, just throw them up in there. 0.50 moles. Oh, no, we did that one already. 15 moles of the H2 divided by the volume. The good news is the volume is always the same for the whole thing. So it's 0.075 molarity. So we're going to take those three values, and those are equilibrium values. So we did say that these are the equilibrium concentrations. So now we can stick those right into your equilibrium law. And we're going to get 0.25 squared divided by 0.020 times 0.075, and that one is raised to the power of 3. And we have to solve that. There's lots of options here, but just be very, very careful about dividing your denominator. Almost every mistake I've ever seen a student make is because they didn't use brackets effectively. Even last semester, we ended up using a calculation app because we found that students were just making so many mistakes. It was just easier to just make sure that they did them in a calculating app. Now, if you have a really nice calculator, you'll be able to keep track of what you're doing visually. So I like using this this Calculator Plus app on my phone and my iPad. It has a nice visualizer. It makes sure that I can see everything that's happening. And so I'm going to equal, and I get some value. It's pretty big value, but that's okay. We're allowed to use big values. And I'm going to just shrink everything down here. Move that over. Okay. And so my final answer here is 7,407. Now, if we're talking about significant figures, we have 2 significant figures throughout. So that would be only the first 2 digits. So we actually should write it out as 7,400. And that will be that. I'm going to leave that up because I'm going to need that calculator in a second. Oh, you guys are not seeing my calculator. That's interesting. Usually that shows up. I guess it's taking over the whole thing. Okay. Well, that's okay. You just weren't seeing the, do you see this when it shows up? No. Okay, that's fine. Because of the projector thing. That's okay. All right, so let's practice another time. Let's do a practice question together. So you have a 2-liter container. It contains this number of moles of NO2, NO, and O2. What is the KEQ? This is assumed to be at equilibrium. So equilibrium law is going to be NO2 squared divided by NO squared times O2, and that is equal to K. Thank you. And then we're going to, we need those values. So we're going to find the concentration of NO2, concentration of NO, concentration of O2. Much like at the beginning of the course, I do like it if you can write down all of your values that you're going to use in a separate area so that we can keep track of them. Make sure that you use the appropriate values. NO2 is 6 moles divided by the 2 liters. So that gives me 3 moles per liter. The NO is 3.0 moles for 2 liters. So that's going to give us 1.5 molarity. And the O2 is 0.20 moles divided by 2 liters. And that gives me 0.1 molarity. I'm just going to go do a little double check around the house for see if I can get some things off the network. Just trying to troubleshoot that stream. I don't know why my streaming is so much worse today than it was yesterday. Does not make much sense. Really, really bad. Okay. All right, so let's just punch those numbers in and see how we're going. So we got the 3 molars squared divided by the 1.5 to the power of 2 times 0.1. These are 0. There's a 0.00 here. And that one is not. So again, we're going to get out our calculator. We're going to go and calculate. I thought you could see my calculator, but you cannot. So I'm just doing my calculator action on the side here. Make sure you use a pair of brackets. For your denominator, and I got a value of 40. Units wise, there probably are units, but they would be a real mess. So these are equilibrium constants. Their value is in the um, in the number, not in its units. So I typically don't even bother putting units in for these. All right, you are given the KEQ, and all but one of the equilibrium concentrations has been calculated. The missing concentration. So here is some algebra fun. So set up your equation first. So we have NO on top squared divided by N square N and raised to no power, and O2 also raised to no power, and that's going to all be equal to K. The concentrations that they have given us for N2 and O2 and NO are, let's see, we were given 0.40 for NO, 0.40 for O2, and no value for NO. Oh, these are respective values, sorry. So this is, watch out for that respectively. So, but we are given a value for K. K is 64 in this example. So what we want to do is we want to do a substitution of every value we can. So 64 goes in here. We do not know what NO is, but we know it's squared. And we do know that we have a 0.40 and a 0.60 down here. So as per algebra rules, we want to multiply as many numbers as we can and simplify as much as possible. So I can't do much with that NO, but I can do some multiplication here of 0.4 and 0.6. And I should get 0.4 times 0.6, so it's 24, 0.24. And then I want to multiply, or however you want to imagine it. You could do, I like to do sort of a multiplication like this, so that both sides are multiplied by the same value, which cancels that out on this side. And I'm now going to do 0.24 times 64. That gives me 15.36, equivalent to NO squared. And now we want to do the square root on both sides to cancel out the square. And so I'm going to take the square root of 15.36, and my value will be not perfect, but 3.92. And that's going to be my value for NO. Looking back, I see that I do have numbers with 3 significant figures, but I do have one that has 2 significant figures, so I should actually rewrite this as 3.9. So there's my 2 significant figures. If you want to go and put that back in the structure here, we can put this as 3.9 molar. How is this feeling, looking, doing? Are you finding it challenging to wrap your head around it? It is a challenging concept, but the good news is you're almost always using the same equation. You got one equation that you build yourself. As long as you can build that equation, then the different types of problems are all kind of based off this very similar equation. It might not be the same. The exponents are going to be different, but they will be similar between the various questions. All right, we have a practice problem right away for that. Maybe I will leave this one for you to try, and I will come back and fill it in so you can check online later today for the answer key. And we will go to the next question. Does that make sense? Or should we do that question together? I think there are 6 different types of questions. So we have, if we want to get them all done, we have quite a few to get through. Let's do the examples. We'll get all the examples done, and then we'll come back and work on the practice questions if we have extra time. I think that might work the best. Okay, so for this example, you are given a reaction and the equilibrium constant, but they are asking you, if you're given the initial concentration, what is the equilibrium concentration? So this is a meat and potatoes question. This is one of the main points that we're doing this whole thing for. So I really want you to be able to do this. I'm really happy to see that we have way more viewers today than we've had earlier in the week. So the later's time schedule is definitely working. Okay, so for the reaction of this and this and this, the equilibrium constant is blah. So what they're saying is that if you take NO squared divided by the concentration of N2 and the concentration of O2, it is equal to 6.76. Okay, that's an interesting observation. Now, if we started, and so one of the things that we like to see is what's called an ice chart. So initial change and then equilibrium. And if we put N2, O2, 2NO, like this, then what they're saying is that they initially have 6 moles in 1 liter of both nitrogen and oxygen. So they have 6 moles per liter, 6 molarity, oxygen and nitrogen, and they have no NO. And then the reaction starts to proceed. And as the reaction proceeds, it will produce equilibrium concentrations that we don't know yet, but these equilibrium concentrations will have to be related to the equilibrium constant. So how much are they going to change by? This is the question. Well, we know that some of the nitrogen and some of the oxygen is going to be consumed to produce some NO. When you don't know a value, what you can do is you can say X. And so we know that some of the nitrogen and some of the oxygen is going to be used up. And that sum of is always going to be the same value, right? Because they react in the same concentration, or the same, they react in the same ratio. So we have a 1-to-1 ratio of the nitrogen and the oxygen. And so we should be losing the same amount of nitrogen and the same amount of oxygen through this reaction. Notice, though, that the amount of nitrogen monoxide being produced is double that of the nitrogen and oxygen. And this comes from this 2 here. So for however much nitrogen I use up, or nitrogen monoxide I produce, I'm going to use up half as much of the nitrogen and half as much of the oxygen. So the result is going to be something like this: 6 minus x and 6 minus x is and 2x are my equilibrium values. So 6 molarity minus a little bit, 6 molarity minus a little bit, and then 2 times that same x value. So let's put those all into our equation and see what happens. So if I put 2x up here, it's going to be squared. And I'm going to put 6 minus x down here, and 6 minus x down here. I'm going to make that all equal to 6.76. If you can get to this point, you have like 99% of the question done. This is really, the rest of this question is going to be largely a math question. And this is the one part of this section I don't like very much, is it's very mathy, and I find it ends up feeling like you're just doing a bunch of math. And I don't, I don't like that. I don't think that I don't think that's the point of a chemistry class, is to make you do a bunch of mathematics questions, but that's sort of what we're at. That's what we have to do here. I'm gonna just check one last thing here, which is, how did I get that? P's. Okay. Oh boy. Hi, John. I'd be up for it, but would it be possible to post an assignment version of the booklet online so I can edit it? Yeah. I'm fine with the paper answers. Will be fine as well. Just take a picture. Paper. Assignment version of the booklet. This booklet, actually, now that I'm thinking about it, yes, for the booklet, I do have an editable version. I'll post. Okay. Making a note. Post editable version. Okay. Oh, someone opened the door. Now it's like cold in here. Nice. Okay. So if you get to this part, this is where it gets challenging. From a math perspective, there's lots of options here to do. In this case, you have two values that are exactly the same being multiplied. So let's go to 2x squared divided by 6 minus x, and that's also going to be squared. And this is where it's, I'm starting to do some, I hope it's not voodoo, but, it does look a little bit wild. There's some pretty fun math tricks that we're going to start pulling off here in a second. Now, what we can do here is we can apply a square root to both sides. This will cancel out both of the squares. And so we're going to end up with 2x over 6 minus x equals the square root of 6.76, which is 2.6. And now you can do some multiplication tricks to bring this to be 2x equals 2.6 times 6 minus x. and and then we have to do some more manipulation. So we're going to get 2.6 times 6. You know, this is where I get kind of, I just start getting bored in a way where I'm like, I didn't come here to do math. I came here to do chemistry. Uh, it makes me sad that this is a big part of our unit. Okay, and now we're getting close. We're getting close to the answer. Let's add 2.6x to both sides. This will give us 4.6x on one side is equal to 15.6. And now we're almost there. We're almost at the answer. 15.6 divided by 4.6 gives us 3.39. X equals 3.39. I guess we should probably make that 3.4. And we're almost there. Almost at the answer. We now have to take this and put it back over here. So 2 times 3.4 is going to be 6.8. 6.8 for the molarity of our NO. We're going to do a subtraction here, so that's going to be 2.6 and 2.6 for our nitrogen and oxygen gas. This is the point where I started allowing students to use Photomath. So with the app Photomath, you can do some real good trickery. So Photomath can do stuff like, now I don't have it drawn out for myself, but what was the problem we had? We had 2x divided by, oops. So we had a fraction, and we had 2x on top, and that was squared, right? So that was squared, and it was divided by 6 minus x, bracket 6 minus x, and this whole thing was equal to, do you remember what the value was? 5.6? Something like that. What are you guys getting there? Yeah. Oh, 6.76. And so from there we can see that the answer is 3.39 is the one that makes sense. We get two answers. One of those answers is 3.39. The other answer is 26. I think that's really, that's a very fast, that's the fastest way you can possibly do these. With Photomath, you can even just write it out on a piece of paper and take a picture of it. You don't have to type it in. And just double check your picture looks good and works out for you. So I'll show you, I'll just write it out on a piece of paper, show you how that works. So if I wrote 2x squared divided by 6 minus x times 6 minus x, especially in this world where you are out on your own and I can't watch anything you're doing, then yeah, I'm worried about the lag too, Dion. Then but now I'm just going to take a picture here, and you can see that it works out the same. So that's one approach, is to just use an app that can solve the equation for you if you're having trouble with these this math. Okay, we have a question, a practice question after that. We'll come back to that in a minute. I just want to get through all the types today if I can. I'm watching the clock there, so we'll see. So if the initial concentrations and an equilibrium concentration are given, then you can also calculate a value of Kq. So for the reaction H2F2 gives 2HF. 1 mole of hydrogen, 1 mole of fluorine are sealed in a flask in a 1 liter flask at 150 degrees and allowed to react. At equilibrium, you have 1.32 moles of HF present. How calculate equilibrium constant? So H2 plus F2 gives us 2HF. Let's write out our initial and our change and our equilibrium values. Luckily, we're dealing with a 1 molar flask, so we started with 1 molar H2. We start with a concentration of 1 molar F2 and no HF. Always assume that you don't have any product unless they tell you otherwise. Some sort of change happened, and then you were left with 1.32 molar HF at the end. The change is always going to be equivalent to the stoichiometry of the equation. So we lose some x's on the reactant side. We gain 2 x's on the product side. If we gain 2 x's, this means that 0 plus 2x is equal to 1.32. So x must be half that. 0 point something. Let's see. 1.32 divided by 2. So 0.66. So we added 0.66, or x was 0.66. So this is plus 2 times 0.66. That means that we lost 0.66 molarity from our F2, and we lost 0.66 molarity from our H2. This leaves us with 0.33 and 0.33. Oh, I guess 34. And now you have a full set of equilibrium values. So this is a fun equation, a fun question type, because you have a lot of things missing at the beginning, but they're actually all there simply through identifying the stoichiometry. So let's write out our equation. We have HF squared divided by H and F2, and that's all equal to K. So 1.32 squared divided by 0.34 times 0.34 is equal to, and then that will be our K value. 1.32 to the power of 2 divided by 0.34 times 0.34, and we get a value of 15 for K. So there's another practice question. I'll go back. Maybe considering the quality of the streaming today, I think I'll make one of those shorter videos where I go through each of the practice questions and go through them more carefully. More carefully, but also more concisely without having to wait for my stream to look like it's healthy again. All right, so we're going to do the last two examples here in the last 9 minutes of class. Let's see if we can get them in there. So a certain amount of NO2 was introduced into a 5-liter container, and when equilibrium was attained according to the equation, the concentration of NO was this. If the KEQ is that, how many moles of NO2 were originally in the vessel? That's an interesting problem. So let's start with our ICE and our equation on top. So 2NO plus O2 changes to 2NO2. And we are given when equilibrium was attained, the concentration of NO is 0.800 molar. All we know, and we know the KEQ value, which is 24.0. Okay. So we have a certain amount of NO2 and 0 NO and O2. At equilibrium, we have a certain amount of NO, but we don't know any other values. Well, one concept to think about is that we know that since we started with 0, we have to be increasing the amount of reactants in this equation. So we're going to be adding x's, and we're going to be losing 2x over here. Well, from this, we can identify that 2x's is 2x equals 0.800. This means that x equals 0.400. So this would have been plus 0.400, which would give us 0.400 as our equilibrium value. We also know that we lost 0.800 to get this final value, but we don't know what that value is. But we do have this value, and KEQ. So now we can solve for this unknown. We know that KEQ is equal to NO2 squared divided by NO squared times O2. So we can do some replacement here, 24.0 NO2 squared divided by 0.800 squared times 0.400. And the result will be some solving here. I'm going to probably end up using some software to solve that. Let me see. I think I have a linear solver on this one. Let's just try that. Yeah, okay. Here, let's go 24.0 equals x. Oh, I cannot do squareds. Switch. If you would like, you could also use Desmos is also another option. Desmos can calculate equations as well, and you can often get away with putting the equation in just as written, and you'll get a result. In this case, I got two values. Looks like 2.4. Does that make sense? I believe it does. Yep. So I end up finding that the concentration of NO2 was 2.48, I guess. So let's put that in here, 2.48. This 2.48 is going to be 8.8 molar larger in the original value as we go up. So we are going to actually have 3.28 is our original molarity. And then notice that it asks how many moles. So we are actually asking, since N over V equals C, then N equals C times the volume. So in this case, 3.28 times the 5 liters. And so the N is going to be equal to 3.28 times 5, which is 16.4 moles. So that's a pretty long route. We are out of time. I do have to start my next class, hopefully not with as many streaming issues as I had this time. But I will produce a video for you that has all of the practice questions worked through in a little bit more of a structured manner. And I'll try to do that tonight. Let me know if you can send me messages through Google Classroom. I will probably post, I'll try to see about, maybe we do 2 classes next week, like a Tuesday and a Thursday, just to see if we can do a check-in and keep things going. I know it is spring break, so there's no requirement for us to hold classes. Certainly you should be entitled to a break, but also it's an unprecedented time where possibly being away from class might feel weird, or being having a nice little bit of regularity or an appointment or a scheduled contact with the outside world might be a nice thing to do. Anyways, certainly would be nice for me. I just want to hang out with you guys. So hopefully that'll work out. I'll post some more comments about that in the in Classroom. Take care, stay safe, and we will talk to you soon.